Alright everybody, what I'd like to do for this video is just kind of wrap up some of the basic concepts that we've been going through of dealing with probability. So we're going to talk just a tiny bit about a couple of things we haven't quite hit on, get some notation. That's really going to be important as you look at the homework. If you're a little confused because you don't understand the notation, don't worry, we're getting there. I really like to talk about what's going on in a situation before I give you all that lovely notation and everything. So a couple of things that we've been dealing with. I'm going to pull up a couple of. Let me pull this guy up. Okay. So, for instance, we talked about a couple of videos ago, this grab bag. I had colored cubes. There were 30 total cubes in the bag. If you don't remember, it's okay. That's why I brought it back out. There were 10 blues, there were 6 yellows, there were 4 reds, 3 purples, 2 oranges, and 5 greens. So, and I had a bowl in the video, not a bag. In class it would be like a brown paper bag, so we couldn't see, but you could do this with marbles. You could do this with different colored candies and stuff like that. So I just happened to have colored cubes with me that day, so that's what we did. We figured out some of the basic probabilities in the video a couple of class periods ago, but we haven't done a lot else with this, and the reason why is I want to ask this question. I want you to think about it. I've mentioned 2 or 3 times now, is something fair? Is something not fair? Okay, so I want to know, is this grab bag fair? Okay, and remember what we said fair means. Fair means that any outcome has the same likelihood or the same chance, the same percentage probability, however you want to think about that, as any other outcome. So in other words, the probability that you get a blue, right, remember that notation, probability of blue, or the probability of getting a yellow, or the probability of getting a purple, should all be the same. If this is fair, these probabilities will actually be equal to each other. Equally as likely to get a blue out of the bag as you are to get a purple. Well, is that true? Well, absolutely not. And we know that because we already figured out some of these probabilities, right? The probability of getting a blue, there were 10 blues out of 30. So we said that that was 10 out of 30, or 1/3. But the probability of getting a yellow, there were 6 yellows out of 30. That's not the same as 10 out of 30. Or when we reduced it, we had 1/5. And certainly 1/3 is bigger than 1/5, right? If I have 1/3 of the pie, I'm going to have more of that pie than if I have 1/5 of the pie. Okay, so, and same goes here for purple. We had 3 out of 30. That was not the same as either of these, and it's only 1/10. So this is much less likely to happen. Only 1 in 10 chances that I'll get a purple, whereas there's 1 in 3 chance that I'll get a blue. So no, this is not fair. Okay, not fair. So I hope you can look at that bag and see for yourself. Things that are fair would be, like, for instance, we talked about flipping a coin. If I had a die that was 6-sided and every side of the die had this different number on it. Okay. Now what if I had something like this? I have a 6-sided die with these options. 1, 2, 2, 4, 5, and 6. For some reason there was a misprint or whatever, and I have 2 2s. Well, now we know that there's 2 out of 6 chances. Probability of getting a 2 is 2 out of 6, whereas the probability of getting, say, a 5 is only 1 out of 6. Or we could say this is 1 out of, you got a 1 in 3 chance of getting a 2, whereas you only have a 1 in 6 chance of getting a 5. Okay, so no, that's not fair. Not fair. Okay. Also, if the die were weighted, they call them loaded dice, right? If it was weighted such that a certain outcome always comes up, then that's not fair. And in fact, there's a project that I can have you work on where you talk about which of these is fair dice and which of these are not fair dice. So that's coming your way, I'm sure. Okay, so these things are not fair. Okay. But we can still do some of the similar stuff that we have done with the fair guys. For instance, the other day we said, what's the probability of having, I think we did 3 girls. Probability of 3 girls. If a family has 3 children, blah, 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 blah. Find the probability of 3 girls, right? Something like that is what we said. Okay, so when we did that, we actually used a tree diagram to kind of help us organize ourselves. And we said, well, that's the outcome girl, 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 right? And we had the path. I don't think I have that tree diagram with me, I'm sorry. But we had the paths marked out, and there were 8 of them. And so this guy was only 1 path out of 8 options, right? Okay, so this was only a 1 in 8 chance. All right, so we're going to do some other stuff where we're going to use these not fair guys, but we're going to use similar techniques as we did with fair stuff, because we said that the probability of having a boy or a girl is approximately equal, right? There's a little bit of genetic stuff going on in there, but normally you've got a 50-50 shot, basically. Okay, oh, let's do this real quickly. What if, let me throw this idea in just to mess with us. What's the probability of not 3 girls? Okay, so the probability that they will have 3 children, but it's not 3 girls. It can be any other number of girls, 0, 1, or 2, but it's not 3. Okay, well, if there was 1 pathway that was all girls out of the 8, then how many pathways are not all girls? There's 7 left over, right? 7 out of the 8 pathways, okay? So an interesting fact we did the other day, we said, well, all of my probabilities are crammed in between 0 and 1, right? Okay. So if I want the probability of not something, then it's pretty easy, and I'll say P because that's what I put there. It's 1 minus the probability of whatever the thing is that I just did. Okay. So in this case, we logicked through it and said, well, there's 1 that is 3 girls, then there must be 7 that aren't 3 girls. But we could also have done it this way. The probability of not 3 girls is the same as 1 minus the probability of having 3 girls. That's what we did. We just didn't mathematically work it out. Well, that's 1 minus 1/8. That's 7/8. And that's what we had, right? Okay, so it works out. You just have to be paying a little bit of attention. One more thing, let me throw this notation in because I said I was going to do this. Notation note. Okay. The probability of not A, let's just say not something, can be written, the probability, that notation can be written, the probability of A with a bar on top of it. Okay, that's universally understood to be not A. Okay, there's a couple of others, and you might see some of these in the book. For instance, probability of A with an apostrophe on it. This basically has happened in recent years because we have a typesetting issue, right? So it's easier to put an apostrophe there than to figure out how to put a bar on top. So some books have gone to doing that, but the kind of traditional way is for not not anything. Normally you would have like a line through something, right? So no smoking, put a line through it. No dogs, put a line through it. No whatever, put a line through it, you know. So that's a similar idea here. This is no whatever the A was, okay. So let's think about that for a second. I want to go back to my grab bag. All right, and we're going to look at some of this stuff, okay. So let's go back to the probability of grabbing a blue cube or marble or piece of candy or whatever it is out of the bag, okay. The probability of getting a blue was 10 out of 30. Does everybody agree? You remember that? There were 10 blues and there were 30 in the box or in the bag, okay. So if the probability of getting a blue is 10 out of 30, if we know that, then find the probability of not a blue. That's my question here. Well, does it matter if this was a fair bag or a not fair bag? Absolutely not, okay? The probability is still going to be 1 minus the probability of blue, okay, which we know was 10 out of 30, okay? Now, you may need to, if you're not really great with fractions and doing subtraction, you may want to go ahead and make this into a common denominator, right? So this one has a 30 on the bottom, this one has a 1 on the bottom, it's 1 over 1. I'm going to make it into a 30. What would 1 be if it had a 30 on bottom? Well, it has to be a 30 on top, right? 30 divided by 30 is 1. Okay, so this is called a well-chosen one. You just have to pick it carefully. Okay, now whenever I've got a common denominator between these guys, I can just do subtract the tops, keep the bottom the same, right? So subtract the numerators, 30 minus 10 is 20. Keep the denominators the same, it's 30. So basically what you did is you got equal size pieces so that the piece size doesn't matter at all. So it's 20 over 30. Or you could go ahead and reduce that to 2/3, right? Okay. You also could have worked with this as 1/3 from the beginning. That would have been fine. 1 minus 1/3 is 2/3. That would have given me that lower fraction. Okay. So we don't really care that they're unfair as far as that goes, this bag. So what I want to do is I want to kind of look at, okay, can we talk about this unfair bag of cubes? Can we look at it and say, all right, what about the tree diagram? Okay, so let's go back to that technique that we had. Okay. Well, let's say that we've got the probability. What's the probability that I draw a blue? Well, we already said that that was 10 out of 30. But what would that look like as a tree diagram? Well, this one actually gets a little complicated because there's a lot of options. So here's draw one cube. That's the event I'm after. Okay, that's the experiment that I'm going to do, and I want to talk about what are all the probabilities. Well, the first one is I get a blue. Okay, what's that guy's probability? We said it was 10 out of 30. I'm going to keep these as out of 30 because I want to make sure they all add up. Later on, if you want to reduce them, it's fine. Okay, what about the next one? So what were all of my options here? Remember, these need to add up to a 1 total. So I had 10 out of 30 for blue. I had 6 out of 30 for yellow. So the next option was a yellow. 6 out of 30. Okay. The next option, I should have started this higher, but whatever, was red. And there were 4 of those guys. So the probability that you'll get a red is 4 out of 30. Okay. My next option here was a purple. And there were 3 of those. Purple, and it's 3 out of 30. All right, I need one more, actually 2 more. Eek. Orange is 2 out of 30. Can I put him up here? I'm sorry. He's kind of out of order, but I'm running out of space down here. Orange was 2 out of 30, and the last option was a green, which would have been 5. Green is 5 out of 30, okay? And again, you want to be able to add these up and make sure they still add up to 30 because total, these are all of my options. This is 100% of my options. So the total probability when I add these up should be a 1, right? So let's double check real quick. 6 and 4 is 10, and 10 is 20. 5 and 3 is 8, plus these two up here is another 10, so that's 30. 30 out of 30. You can double check me, write it out, put it on a calculator, that kind of thing. But we've got them all, and we add up to a 1, which is good. Okay, so then let's talk about what we just did a minute ago. What's the probability of not blue? Well, the probability of blue is 10 out of 30, then I should be able to come through here and say, here's all my other probabilities, right? And add those up, and I should get the 20 out of 30. I should be able to see that. 2/3, okay? The other thing I can do at this point is I can say, well, what's the probability that I draw blue, and then I put it back in the bag? So all of those independent versus dependent events. Okay, probability that you get a blue and a blue with replacement. Let's talk about that. Let's remember if we remember. Okay, if I draw blue out, but then I put it back in the bag, then did I change the number of cubes that are in there? No, there's still 30 cubes, right? And did I change the number of blues that are in there? No, there's still 10 blues, right? So with replacement, these are independent events. Remember what that means. It means that the first event and the second event do not rely on each other. So it doesn't matter what happened with the first event, the second event still has the same probability. So the probability of blue here is, remember how we did that? We want a blue in the first one, and we want a blue in the second one. So that's a multiply, right? And is multiply. Remember that? Okay, so that would be a 10 out of 30 times a 10 out of 30, or a 1/3 times a 1/3. I'll go ahead and reduce those, makes my life easier to do the math. That's a 1 in 9 chance, right? The probability of getting a blue, putting that guy back in, and then getting another blue actually happens 1 in every 9 times. Now, that's actually a pretty good amount considering that I got 2 different guys, right? 2 different blues out. But remember that this was a huge percentage chance to begin with. It's actually the biggest of any of my options here. Okay. Notice that my probabilities in here are not the same because it's not a fair bag. So we can do it just like we did it with the children, or just like you would do with the dice throws, or just like you would do with a coin flip, that kind of thing. But we just make sure that each one gets its own probability in there. Okay. On a test, I wouldn't give you one with this many, things going on. I might give you 3 different ones, but they might still have 3 different probabilities. Those 3 probabilities would add up to a whole 1, because that would be all my options for that particular situation. But yeah, so it just wouldn't be this crazy. All right. Then what was the other one we did? What if they are dependent? Probability of a blue and a blue without replacement, meaning that I keep out that first guy, right? Now just think about that for a second. Do we think it's more likely or less likely that we'll get 2 blues if I keep one of them? Hopefully in my head I hear you saying, well, it's less likely because you kept one of the blues, so now you only have 2, or what do I have, 9 instead of the 10 that I had. So I have a smaller probability of getting the other one as a blue. Okay, so without replacement, that's a dependent situation, meaning the second blue depends the second blue depends on the first one. It relies on it. But blue and blue still means multiply, right? Because it's still an and statement here. Okay, I want a blue and I want another blue. Okay, so the difference here, it's still going to look similar to what we had here, the probability of blue and blue without replacement. It still starts out, the first guy's still 10 out of 30, right? And it's still multiply because it's still a blue and a blue. What's going to change is this second probability. Okay, let's think about it. There were 10 blues in there. I drew a blue and I kept it. How many blues are in there now? In my head, I hear you say, 9. 10 minus 1 is 9. Okay. And then there are 30 total cubes, but I kept the first one that I drew. So what about that? There were 30. I kept one. In the second probability here, it's only a 9 in 29 chance, right? All right. Now, I can still reduce this 10 out of 30 to be a 1/3. And I can still multiply straight across the top, straight across the bottom. I don't have to have a common denominator when I multiply. 1 times 9 is going to be 9, and 3 times 29, oh my goodness, what is that? 7, 6, 87, is that right? Okay. All right, so, and I don't know exactly what that is. I don't have a calculator. Where's the calculator? Hang on. I do have a calculator. All right, so let's figure that as a decimal because that's going to be a little bit easier maybe to compare. In my head, I'm thinking 9 out of 81 would have been 1/9, right? But this is 87, so it's splitting it a little bit more, so it's less likely than the other one. I'm going to do up here, what's 1/9 first? This was an 11.1% chance. Okay, that's the probability for that guy. This one over here, 9 out of 87, is approximately 10.3% chance. Okay, so if you are having a problem comparing fractions, especially if they don't have a common denominator, you could get a common denominator, that would be fine, but sometimes like here with 87 as my denominator, that's an ugly guy, right? Ugly denominator, we don't want to work with that one. With the other denominator being a 9, that's kind of nasty. Okay, so sometimes when it gets ugly like that, you might just switch over to percentages. We know how to do that. And or decimals, you could have done a decimal, 0.111, 0.103, but we can look and say, oh, you've got an 11% chance of doing blue-blue, drawing blue-blue out of the bag here, but you only have basically a 10% chance of drawing blue-blue out of the bag if you keep that extra blue. If you, without replacement, you keep it out. Okay, so the techniques are the same as they were for the fair situations, but they look a little bit different because whenever I do this, this second probability is going to change. Now, the first probability is always the same because that's the same grab bag, right? It doesn't matter. There were 10 blues, so it's still 10 out of 30, no big deal. But the second probability is the one that's going to change on me. All right, so let's see what else we got. The other situation that we had the other day, whenever we had unfair, was the spinner. I'm not going to do a lot with that. I just want you to take a look at that and see. So, for instance, the A was 50%. Actually, the B that we were working with was 25%, right? And the C and D were 12.5%. So they were not fair spinners. This is still not a fair spinner the way I have it anyway. So not a fair spinner, so make sure that you think about those if you have a spinner question, right? Okay. Let's see. I want to talk just a tiny bit about this other situation that we might run into. And I'm just going to probably show it to you so that we can look at it. But so real quickly, just to define something, what is not fair? Okay, loaded dice, spinners that aren't split evenly, a coin with 2 heads on it. I almost always have a student in my class who'll say that one because they've seen coins with 2 heads on them, that kind of thing. Maybe grab bags, M&M bags, marbles, etc. might be unfair. Now, I can make you a grab bag that is fair, right? I could put in 3 yellow, 3 blue, and 3 green, and you'll have 3 out of 9, 3 out of 9, 3 out of 9, and same probability for each of them. So you just have to kind of think about it. It's not that it is unfair, it's just that it might be unfair. Now, these guys up here, loaded dice, spinners that aren't split even, those are not fair, right? Sometimes if we're talking about somebody's personal technique, something that they did, any of that. But basically the statistical answer is whenever one outcome has a greater probability of occurring than the others, you have an unfair situation. Okay, that's what you need to keep in mind. So there's lots of situations where that might happen, but that's what we're looking at. So bag of marbles, not fair. Okay. Let's see. I don't want to do that right now. Just suffice it to say that if we were doing some of these problems, we might put them on a tree diagram, and you can see by the one I just did, I only did one situation, right? Drawing one bag or one cube out of the bag, and it got kind of complicated. And depending on how many options you have, I'm just going to throw this guy up here. Depending on how many options you have, it could get really messy really fast. So this is a tree diagram I did in a different class where we were doing M&Ms, and it was probability of getting a red and then a red, okay? And the probability of getting a red was 8/17, and there were 17 candies in there. I was nicer to you guys. I made 30, so it was easily reduced. Probability of getting a blue was 6/17, and probability of getting a green was 3/17. Okay, so, and apparently this was without replacement. So we might have to look at that over and over again. So let's think about that. If I had pulled the red the first time, and if its probability was 8/17, then on the second pull, the probability is 7/16, right? I reduced the top by 1, and I reduced the bottom by 1. But think about it. If I pulled a red the first time, but then here on the split, if I did red and then blue, the 6/16, what's that about? So the top didn't change because I didn't pull a blue out the first time, but the bottom did change because I kept that particular, the red guy that I pulled out first. So sometimes it gets a little bit complicated. Also here, my original probability for getting a green was 3/17. But here, as I follow through, I got a red the first time and then a green. I still have 3 green guys in there, right? But I don't have 17 M&Ms anymore. I only have 16 M&Ms. So I kept one of the reds out. I didn't change the number of greens, but I did change the total. So sometimes that happens. Like you might get both. You might change both. Like we changed the top and the bottom when I went from red to red. But here, I only changed the bottom when I went from red to blue, okay? So sometimes it just works a little differently. You just have to be aware of that. On all of them, though, notice that once I keep one red guy out in this case, then I always have the 16th for the bottom. Okay. If I kept a blue out, if it was the blue-red guy, okay, that was my option, then I pulled one out, the bottoms are all 16 because I kept that blue. Okay. On this one, though, where I went blue first, notice that the top of the red doesn't change because I didn't pull out a red, I pulled out a blue. But the top of the blue does change here. So it gets a little complicated as you do some of these. You'll have to kind of think seriously about what's going on. And whether or not we're in a fair situation, whether or not the top changes, the bottom changes, or both. So sometimes you have top changing, sometimes you have bottom changing, sometimes you have both. So really, really, really pay attention if you have a dependent situation. That's what I'm getting at. Especially with these unfair guys. That's important. Okay. I want to talk about roulette wheels. Because one of the big things about statistics, and I don't know why, but you always have gambling involved, okay? Well, I do know why, because there are a lot of statistics in gambling. I usually like to kind of stick more with sports and stuff like that, but those statistics can get really complicated, so I don't want to mess with them too much. So if you're not familiar with casinos and you're not a big gambler, which I'm not personally, you might not know a lot about a roulette wheel. You probably know, like I did, that there's red and black, right? Okay, so you get red options and you get black options. So here's the deal with it. There are 38 numbers on a roulette wheel. Okay, 38. And contrary to popular belief, it is not half red and half black. Uh-oh. So there are 18 red numbers and there are 18 black numbers. Okay, well, if you add that up, you only have 36, right? So there's two other numbers on those, and if you're not aware, there's a 0 on one side of the wheel and a double 0 on the other side of the wheel, and they are green. Two green numbers. 0 and double zeros. Okay, so you can bet a lot of ways, and there's tons of stuff that you can do with a roulette wheel, but like sometimes people will say, oh, if you're going to Vegas, bet on, whatever. Bet on number 21 for me because I just turned 21 or whatever. So you might have people that want that. Or, oh, my favorite color is red, so bet on red. Okay, so if you bet on red, it's red in general. Okay, you have pretty good odds of getting a red, right? So let's do that. Let's do the probability for that. Probability of getting a red is what? 18 reds, so that's the outcomes I'm after. And how many possible numbers could I land on? 38, right? So it's 18 out of 38 is my overall possibility, right? If you reduce that, which they're both divisible by 9, you get 9, or by 2, sorry, you get 9 out of 19. Or if you wanted the percentage chance, it's like 0.4736, which is 47.36%. Right? All of those are equivalent. Okay. So, do I have a 50-50 shot of winning if I bet on red? Actually, the answer is no. It's less than 50%. It's 47.36. And if you've ever heard the saying, the house always wins, this is why. Even with the best possible outcome, which here would be, either 18 reds or 18 blacks, if you bet on red or you bet on black, it doesn't matter. And the probability of black is the same, right? Because they have the same numbers. So I didn't do that one, but same thing. Still 47.36%. Okay, so even if I bet on red or even if I bet on black, my probability of winning is 47.36. What's the probability of the house winning? The house winning, that's what they call the casino, right? Probability that the casino wins if I bet on, say, red. Okay, well, I hope you're thinking in your head, that's 1 minus, because this is not, I'm not winning, the house is winning, right? 1 minus, what was my probability of winning with a red? 9 out of 19. I don't want to deal with those decimals. Okay, so that's a 19 over 19 minus 9 over 19, right? Get a common denominator. Subtract 10 out of 19. Okay, and I don't know what percentage that is. Let me look at it. Sorry. I didn't figure that one out before I came. 10 out of 19 is a 52.6% chance, basically. So it's a rounding thing, right? This was, if they rounded this one, they must have rounded this one to 47.4. It's probably something in my calculator that's got a only going to one decimal thing, so. All right, so if you subtracted it out, they've got a better than 50% chance. So the house always wins. That's what they say. Okay. Now, here's the deal. What if, so let's just say that I sit there for a really long time because I just want to win. What's the probability of, not probability. Here's what I want to know. If I sit there while the wheel spins 100,000 times, how many reds should we expect? There's that word again, expect. It's an expected value. Think about that for a second. Okay, and in my head I'm hearing you say, well, if I get this much, 47%, let's use the decimal, 0.4736 for one spin, if that's my probability for getting one spin, and you want me to do this 100,000 times, how many of those spins are going to be red? Expected, right? We understand that empirically speaking, if I actually sit there and watch the wheel spin 100,000 times, it might not be this, but how many can I expect it to be? Well, in my head, I'm hoping you're saying that, well, we think it'll be 47,360. And in my notes, I actually had that this was a decimal. The decimal was bigger than this. So 47,368.4 if you didn't round above. A couple of you have asked me questions about rounding, and normally it's better to wait until the end to round. I clearly rounded early here. So this is if you rounded early, this is if you held on to that decimal, which was actually 0.47384. If you held on to that decimal, then you'd have that. All right, let's see. If somebody tells you the probability that it's going to rain this weekend is 17%, then what is the probability it won't rain? And I'm going to use our notation. Probability of rain with a bar over it. That is really light. Sorry about that. What is that? Okay, so hopefully you're thinking about it. I'm hoping you're thinking about it. And in my head, I hear you saying, oh, well, what we're going to do there is we're going to subtract from 1, right? Well, how do I subtract a 17% from a 1? Well, the answer is whenever you're dealing with the percentages, you'll do 100% minus 17%, right? Okay, which in my head looks like 83%. Okay, if you didn't switch, because we're dealing with percentages here, if I don't switch this first number over to 100%, then I'm doing 1 minus 17%, that doesn't make sense, right? So if you don't want to, this is with percentages. If you don't want to do that, if you still want to do that whole rule that we had for 1 minus the thing, this is with the decimal. 1 minus what? What would this be as a decimal? Move it 2 spots. 0.17, right? And that would be 0.83. Okay? So I just want to throw that out there to be aware that, okay, we said the probability of a not something was subtract from 1, but if they give it to me as a percentage, then I'm going to talk about 1 or the whole or 100%, right? Those are all kind of equivalent concepts in our minds. So if they gave it to me as a percentage, then yeah, I want to make sure that I work with it as a percentage. Okay, let's see what else we got. I want to say, I've mentioned before this law of large numbers, right? That whenever you do this experiment a million times, that we expect for our probability to come out close to the theoretical. Our experimental probability to be close to the theoretical probability. So I want you to keep that in mind. For us, we have that expected value thing coming in over and over and over again. So I want to make sure we have just a little bit of an idea of how that happens. So we keep on saying expected, 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 and a lot of times we just have one outcome that we're looking at. So it's a weighted average, right? It's always a weighted average. And for one event, no big deal, we want the probability of the event, okay, the probability of getting that thing, times whatever the value is that we'll get from that thing. Okay, so what does that mean? Well, say that I want the expected value for whether or not I'm going to win in a lottery. Okay, well, there's the probability that I'll get that win, whatever, it's a really small probability, right? Times the value that I'll win. Well, maybe I'm going to win $1 million, right? So, and we'll do this probability in a second. The problem is that a lot of times it's not just that probability. Okay, there's actually, this is event number 1, right? Sometimes we have a different event that could happen. Okay, and this is value number 1, this is value number 2. So there's a different event and a different probability and a different value for that thing. Okay, what I'm going to do is I'm always, whenever I'm doing these expected values, I'm going to figure out what's that event, what's that value, and multiply them. But I want this thing to happen or this thing, right? Now remind me, whenever we said or, what did we say we did? So or means almost 100% of the time add, right? So we're going to add those. So here's what I mean by what's going on with this probability thing, with this lottery thing. So here we go. An expected value from a lottery. Here's what it says. If you have a 1 in 80,089,128, that's my probability of winning $30 million. Okay, so that would be my win. This is your probability of winning. Probability number 1, and I'm going to multiply it by the value, number 1. Okay, that's my first probability of winning. But a lot of times, then, whenever you're doing these lotteries, maybe there's a 1 in 1,953,393. Sorry about that, it's a big number. Maybe that's the probability that instead of winning the $30 million, I'll just win $100,000. Okay, this is the second probability. And this is the value you would win in that second instance. Okay, so there's a lot of different things going on. By the way, this is not a fair situation at all, right? Be aware of that, because it's not the same probability for me to win $30 million as the probability for me to win $100,000, right? So if I had that, and there are other probabilities and other things, maybe there's a $5,000 win, maybe there's a $100 win, so on and so forth, I would just keep on adding those probabilities over and over and over. And that particular lottery costs you $1. It's a scratch off. I don't know. Okay. What's the probability that I'm going to spend that $1 if I'm playing this lottery, which I'm probably never going to do? Okay. It's 100% probability that I'm going to spend that, right? You can't play, you can't win if you don't spend the dollar, right? So the probability for me to, whatever, we'll call it probability number 3. The probability for me to spend that dollar is 100%, or a 1. And in that case, I'll lose $1, right? So if I don't win any of this, if I don't win at all, which is kind of what I assume is going to happen when I gamble, I for sure lose my $1. Does everybody agree with that? Okay. So what would you do? You'd multiply these together, add, multiply these together, add, and that would be a negative $1, right? Well, in this simplified case of my really cheesy lottery here, you would worry about what's going on there. Let me do this math real quick on my handy dandy calculator. 1 divided by 80089,128. This was a problem out of a book I found, and it doesn't even think it's like a less than 0.000% probability, times 30 million. 1, 2, 3. Okay, that weighted value for this thing to happen is 0.375. Okay, that's pretty good. What about this guy? 1 divided by 1,953,393. Crazy numbers in the book. It's not my fault. I'm sorry. Again, they think that's a less than 0.000% probability. Let's multiply that by the 100,000. Okay. Oh, that was only, hang on. I think that was, oh man. Let me start over. I'm sorry. I think that was only 10,000, but I want to make sure. Divided by 1,953,393. Okay. That's that crazy decimal. Times 100,000. There we go. Okay. 0.051. Well, that's looking pretty good too, right? That's like a 5-ish% chance. That's not terrible. Or that's the weighted value. That's the expected value here. So that would be like 5 cents, I should say. So maybe I should get 37 cents here. Maybe I should get 5 cents here. But here's my value. Here's my expected value. I'm definitely losing $1. Does everybody agree? Definitely a -1 here. So as I look at that, I'm like, oh, well, let me take this guy that I already had there and let me add 0.375. Well, that looks pretty good because, that's 0.426. But now let me subtract my $1. My expected value whenever I play in a lottery, and by the way, this is actually true, they expect you to lose, on average, somebody will lose 57 cents. Well, that's not bad, okay, but that's what you're expected to get. Expected value. Because I did the probability times the value, right? So my expected value is I'm going to lose, okay? And that's what most people should expect if they're trying to play the lottery, okay? That's just the way it is. So expecting to lose here, I'm going to lose 57 cents on average. What that means is, okay, occasionally I might win $5 off that scratch off, or somebody might get $100 or $500, but in general, most people aren't winning this $30 million prize, right? In general, most people aren't winning the $100,000 prize. Most people are losing their dollar. Okay, that's what it boils down to. And it has to be, because if you don't, everybody doesn't lose the dollar. If most people don't lose the dollar, then they can't run the lottery, right? They need lots of people to lose the dollar, and occasionally somebody will win. But in general, it's 1 out of 80 million people, or 80 million scratch-offs, or whatever this is, that are going to win that $30 million. So it's actually very unlikely that you're going to do that. All right. So just had to throw that expected value in there. Remember that expected value almost always comes from unfair situations, right? This is not fair at all. And I think that's it. We've got one more little concept of probability, which is how to do these combined probabilities, the ands and the ors and stuff like that. I'm going to do another video on that just to make sure we're really solid on ands and ors. And what if, by the way, we have overlapping situations? We haven't done that yet. So far it's been like I roll the die, I get a 6, I roll the die, I get a 5. But what if it's something like, oh, I'm in the classroom and I see a bunch of people who have hats on, and I see a bunch of people who have glasses on, and what is the probability that somebody has a hat and a glasses? Ooh, both. So it's an overlapping situation, because you can have both. So we're going to talk about those in the next video. All of that kind of stuff's coming up. All right, thanks. Let me know if you have questions.